for being here. The next talk is Jacob, probably I did it wrong, Gru Simonsen, and it is a pre-recorded video, so please tell me if everything goes right. And after the video, you can discuss with Jacob if you have any question.
Welcome all, and thank you for attending my talk on the expressive power of one variable used once, with the subtitle The Chomsky Hierarchy and First-Order Monadic Constructor Rewriting. This talk is going to be what I'd like to call a completionist's view of the expressive power of rewriting, and you'll get the explanation of what I mean by completionist in a moment. So, for expressive power, we all know that term rewriting is Turing complete. So under suitable encoding, any Turing machine M and its input I can be coded as a term T, where termination or acceptance or rejection of M on the input I is equivalent to some kind of rewriting property of T. And there are endless variations of the above. So we can talk about the expressive power of restricted notions of term rewriting, or expressive power of term rewriting with different sorts of symbols, like in constructor rewriting, where you have both defined symbols and constructor symbols. And there are basically many, many variations. So one particular variation that has been of very high interest in the last 20 years is called implicit complexity. So this is essentially the study of restricted rewriting systems, all programming languages, and their expressive power. Are they Turing complete? Can they express, say, complexity classes such as p-time, in the sense that any p-time computable function or any p-time decidable set can be decided by some rewriting property of a restricted system, and conversely, every function or every set decided by a particular restricted rewriting system, does that lie in p-time? So this is essentially implicit complexity. A typical result is that certain restrictions on the rewriting systems, typically syntactic restrictions on term or rule formations, or semantic restrictions on evaluation orders, correspond to the rewriting system computing exactly the polytime computable functions. And there's nothing special about polynomial time. It could be polynomial space, exponential time, it could be something else. And this is typically investigated for constructor rewriting due to the nice separation between program, right, the defined symbols, and the data, the constructor symbols, at least in rewriting. And this also corresponds very nicely to programming language intuition. So what do we do in this paper? Well, I take a completionist view. So completionist in the video game sense. In video games, a completionist is a person who wants to collect all the hats or get all the Pokemon and so on, while most people just finish the story or complete the game. A completionist wants all the achievements, right? They want to investigate all the nooks and crannies. And what I'd like to do is I like to think about some of the syntactic techniques or syntactic restrictions that have been shown to be effective for characterizing complexity classes by constructor rewriting systems, and then kind of push them to some of the limits or do some restrictions that we're not quite used to do. And one natural question to ask is, what happens if all symbols have arity at most 1, right? So all functions are either nullary or unary. So we cannot really duplicate inputs or arguments to function symbols. So clearly something is very, very restricted. And for constructor rewriting, well, what we get will essentially be a variation of two-sorted string rewriting. Two-sorted because we have defined symbols and constructor symbols in constructor rewriting. It's not quite two-sorted string rewriting. There are other syntactic restrictions that we have when we do constructor rewriting, but it looks very much like it. And let me also say that the title of this talk and the title of the paper includes the word monadic. And by monadic, I mean every function has arity at most 1. So there's no relation to Leibnizian monads or categorical monads or programming monads. And there's also no restrictions or no relation, sorry, to monadic string rewriting systems, which is something else. So in that sense, the title might not be very well chosen because it gets people the wrong idea. The use of monadic, we have to talk about arities at most 1. That's basically what's done in logic. So monadic systems are typically ones where relations and functions have arities 1. which is why I chose that word. And the object of study we look at in this paper is the Chomsky hierarchy. The Chomsky hierarchy of languages, because it's well known and corresponds in obvious ways or very natural ways to existing restrictions from implicit complexity. So let's first have some definitions and rules of the game. Just to remind you of what a constructor rewriting system is, we have partitioned the set of function symbols into two disjoint sets, the set of F of defined symbols and the set C of constructor symbols. You can think of these as kind of function names for defined symbols and data for the constructor symbols. And a constructor TRS, constructor term rewriting system, is a term rewriting system where the left-hand side satisfies that there is a defined symbol at the root, and then that defined symbol has a number of arguments. So in a monadic system, it has exactly one, that are all constructor terms. So they only consist of constructors and variables, right? So it looks very much like the left-hand side of a definition clause in a functional programming language. I need to define what I mean by a constructor system characterizing a set of strings, essentially. So let's do that. Let's take an alphabet. And by an alphabet, I just mean an alphabet of symbols that essentially have nullariarity, right? So it's like in the language game, we have the letters A, B, C, D, E, F, G, and so on. And then we have a nullary constructor symbol like this, like a little wedge. You can think of this as a string terminator. So basically what we do, we take any string, A1 to AN, over the alphabet, and then we create a constructor term. We can create a constructor term by taking a particular unary constructor for every element in the alphabet, and then we put the string terminator on here at bottommost, basically. So that's it. And of course, the empty string is denoted by basically the string terminator. And this is just a way of looking at strings as very, very simple constructor terms. Now, imagine that you want to characterize a language. So let's take a language. So we have an alphabet and a constructor TRS. And let's assume that what we just did, the little trick we just did with alphabets, where we took a constructor symbol for each letter in the alphabet and also created a string terminator symbol. Let's assume that that's a subset of the set of constructors, just so we have them available. Then we say that if we have a language L, which is a subset of the set of strings over the alphabet A, so a language in the usual sense, then the constructor TRS is set to accept that language if there is a particular defined symbol here called F0, also called the start function in the literature, such that if we take any string over the alphabet and take its constructor analog, right? So we translate it to the simple constructor term I just showed you before, and then we supply that as the argument to the start symbol, then there is a rewrite sequence that reduces to the string terminator, right? So basically we eat through all of the input, and when we're done, we have accepted. Of course, there might not necessarily for all such strings alpha here be a reduction like this, in which case the constructor TRS does not accept. So this is a fairly standard notion of acceptance in the world of implicit complexity. And let me just note that this particular thing with the term reducing to the string terminator, we can in general replace the string terminator here in this definition by any other term. It does get really complicated to do so in case we have some extremely restricted constructor term rewriting systems that's characterized the context-free languages or regular languages. And the paper basically glosses over that point. For now, this is the definition. So the fundamental question we want to investigate is what classes of languages are accepted by what types of monadic constructor term rewriting systems. So this is the definition of acceptance. So we need to find out what kind of restrictions can we make that will allow us to accept exactly the languages in well-known classes. So let's do that. Let's just remind ourselves of the Chomsky or Chomsky-Schützenberger hierarchy. This is essentially just a classification of recursively enumerable languages. So Each of these 4 classes in the Chomsky hierarchy, the recursively enumerable languages, the context-sensitive languages, the context-free languages, and the regular languages, right? The 4 standard classes of the Chomsky hierarchy, they have particular classes of grammars that exactly expresses or have the expressive power necessary and sufficient to actually characterize the language in the class. And each of the classes here in the Chomsky hierarchy has a canonical corresponding machine that accepts them, right? So for recursively enumerable languages, these are the Turing machines, and for regular languages, all the way down here, they are essential DFAs and NFAs. So this is the standard setup. This is typically something you learn in an initial compiler course. So in the paper, we show that particular restrictions on monadic constructor term rewriting systems correspond exactly to the classes in the Chomsky hierarchy, in the sense that each class is characterized by these monadic constructor TRSs. So for each element, for instance, for each recursively enumerable language, you can find an unrestricted monadic constructor TRS that accepts it. Conversely, if you have an unrestricted monadic constructor TRS, there will be the language it recognizes or accepts will be recursively enumerable. So the restrictions on rules we have are as follows. I'll just real quickly walk you through them. So the set of recursively enumerable languages, well, you just don't have any restrictions on the rules. None are necessary, and this is pretty standard. As you can see here, I've written that this is well known. So for the set of context-sensitive languages, basically you again do something that seems completely obvious. You have a restriction that says that the right-hand side, whatever it is composed of, with symbols and so on, is at most as long as the left-hand side. So it's non-length increasing. But the interesting bit from the point of view of implicit complexity are the 2 final ones here, the context-free languages and the regular languages. So basically, these correspond to monadic constructor TRSs that, in the case of context-free languages, are what's called cons-free. And I've written here strongly cons-free that I'll explain in a moment. So strong cons-freeness is a simpler condition than what is typically called cons-freeness in the literature. And if you then force those strongly cons-free constructor term rewriting systems to also be tail recursive, I'll also explain that later, but it corresponds very well to programming intuition, then you characterize exactly the regular languages. So let me just real quickly explain the notion of cons-freeness here by some examples. Cons-freeness means that if you have a rule, L goes to R, the right-hand side contains no constructor symbols. You cannot build new data. What you can do, of course, is have constructor symbols in the left-hand side that you kind of eat, right? If you apply a rule with a constructor symbol in the left-hand side and there's no constructor symbol in the right-hand side, you essentially destroy a constructor symbol, and you cannot build new data. So that's it, basically. And cons-freeness has been used for many different implicit characterizations. So let's just give you a few intuitions. Basically, the keys to all the results are the same. If you have a monadic constructor rewriting system, you also have a syntactic separation, or border, if you will, between 2 kinds of symbols in the left-hand sides of rules. So even in completely unrestricted systems, so a rule may look like this. You have some defined symbols. These are the non-bold symbols here in the left-hand side. And then you have a constructor term. So you might have some constructors here, etc., and then a variable. So there's a very well-defined border here in the rule between defined symbols and constructor symbols. And in the right-hand side, well, you can just mix them up. So there are no real restrictions. Now, if you want to simulate restricted constructor systems by machines, for instance, Turing machines or linear bounded automata, you can usually do that without worrying about these mixed symbols in the right-hand side, even though they look a bit out of place. If you want to go the other way, if you want to simulate machines like Turing machines or push-down automata by rules, you can actually strengthen the observations from before. There will be a well-defined border also in the right-hand side, because if you take something like cons-freeness, where you don't introduce new constructor symbols, well, then there's nothing mixed over here in the right-hand side. You just have literally a bunch of defined symbols and maybe a variable. So an easy consequence of this is that if you look at what a term looks like down here, I've tried to paint a little picture here. You have like a stack or string of defined symbols, and then you have constructor symbols to its right, and then all redexes must happen here at the border. So if you then rewrite the regex, well, you cannot introduce new constructor symbols. So the border, there's still a border. You can maybe shrink the stack of constructor symbols a bit, but there's still a border. So everything becomes kind of manipulation of two stacks. And even if you don't have const-freeness, if you want to do some simulation, you can often do tricks like this such that everything becomes manipulation of two stacks. Now, there are some complications. Sometimes in implicit rewriting, you do something that's not necessarily in the rewriting spirit. You say that systems have to be use innermost reduction or call by value or something like this. And I don't want to do that. I want to have unrestricted rule applications. Now, even in constructor systems, you can have rules that look like this. So X is a constructor term. So this is a valid left-hand side of a constructor rewriting system. Now, since there are no constructors, you can actually have redexes of rules that looks like this happen inside the stack of defined symbols and not at the border. And that, of course, messes things up. And this is the typical price to pay for rewriting type characterizations without specification of innermost reduction or call by value. But I don't want to impose innermost valuations. So the crucial observations here, and these require a bit of work in the paper, is that it does not really matter when we try to simulate things like Turing machines by constructor TRSs. And conversely, when simulating constructor TRSs by machines, it doesn't matter for things like Turing machines that are really powerful. And for less powerful machines, unfortunately, like push-down automata or deterministic finite automata, we have to roll up our sleeves and say, these steps here can be postponed. We can do all of the things at the border first, and then eventually this regex, if it still exists, will be down at the border. Okay, so let me just real quick tell you about the specific arguments for each class of language for recursively enumerable languages. So those where we have that we can simulate without any restrictions on the constructor systems we're looking at. You just do what we've known for 50 years. These kinds of simulations have been standard since the 1970s. Now, in the paper, I kind of do the whole thing, right? I show in all details how it's done. So this here is a typical definition of what a constructor rewriting system that simulates a particular Turing machine M here should look like. And it might look complicated. It really isn't. This is completely standard. And conversely, if you want to simulate a constructor system by a Turing machine, this is also standard. You have a finite set of rules, you have a finite set of defined symbols, and so on. So that's basically easy. For context-sensitive languages, those that are characterized by non-length increasing constructor systems, we note that, well, the class of context-free languages is identical to the complexity class called NLin space. So the class of languages recognized by linear bounded automata. A linear bounded automata is a non-deterministic Turing machine that uses space, a constant times the size of the input, basically. So that's it. Oh, but then we can actually just use the previous simulation I just showed you for Turing machines and then manipulate it a bit to take account of differences in alphabet size and so on, to allow simulation of Turing machines only using linear space, right? So we basically constrain the size of the work tape by manipulating the constructor term rewriting systems a bit. And then from there on, that's easy. Conversely, simulating a non-length increasing constructor system by a linear bounded automaton, that's also pretty straightforward. So these things are fairly well known, maybe not in quite the syntactic setup that we have here, but essentially it's something that's been done mutatis mutandis a lot before. For context-free languages, well, we do these by characterizing them by strongly const-free constructor systems. Now, a constructor system is said to be strongly const-free if for every rule, So left-hand side goes to right-hand side. There are no constructor symbols in the right-hand side. I hope you will agree with me that this is an extremely simple, clean definition. The reason I call this strongly cons-free is that when you look at the term cons-free in the literature, typically it's a bit more liberal. What you can do is you can have, for instance, some constants in the right-hand side, or you have some requirements that every constructor term that occurs in the right-hand side should be a subterm or something that occurs in the left-hand side. And this is slightly more complicated. And I like the very clean definition. Now, if you do the usual cons-free definition that sometimes in literature, this gets extremely messy in constructor term rewriting systems. And I really, really like this simple characterization. So I had to call it strongly cons-free just to show the difference. And that's been used both in rewriting and functional programming for characterization of multiple complexity classes. Pardon the spelling error here, multiple complexity classes since Neil Jones's pioneering work in 1997. Now, if you remember my picture from before, here with the two stacks, where this is the defined symbols and this is the constructor symbols. Basically, if you contract the radix here, the constructor stack can never grow, and all constructors that are in it here after the reduction were already in the original stack in the same order. So the defined stack can grow and shrink like a normal stack, but the constructor stack looks very much like a one-way read-only input tape. Now, if you remember your undergraduate course in formal languages, or something equivalent, this is essentially the definition of, or a description of, a push-down automaton, right? A machine that has a one-way input where it sort of eats a symbol at the time, but has a secondary stack, an auxiliary stack that it can manipulate. This looks just like this, just put together differently. And that's the whole key. So you can basically do simulations like this back and forth, but multiple housekeeping lemmas are needed to handle radixes that are in here. There are some proofs in this part of the paper that could be done much more easily by appealing to results in formal grammars. But I have kept this more involved proofs that I have with stacks, because I like to use the same intuition for all language classes in the paper. I think this is much more pedagogical. I also think this is a lot cleaner. But you can probably actually prove some of the results for context-free languages here much more quickly by grammars. And for regular languages, well, these are characterized by tail recursive strongly cons-free CTISs. Now, what is tail recursive? Well, you have a pre-order on the set of defined symbols. And if you have a rule that looks like this, so here f of w goes to right-hand side, and you have some defined symbol in the right-hand side, then that defined symbol cannot be strictly larger than this symbol at the root. Now, if you do termination analysis, this looks very much like a termination order. It's not. It's just a pre-order, and the restrictions are fairly weak. This is completely standard, also in the rewriting literature, a completely standard definition of what tail recursive means. It corresponds to the usual intuition from programming, where the tail call is the last call. You're calling the function that you're defining, basically. So you can think of the last call now, that should be of f, or it should be something that is on the same sort of level in the pre-order of f. You cannot have any kind of hidden recursion where some function inside here, the right-hand side, calls f again after a few recursive calls. Basically, that's what happens here in tail recursion, that you prevent this. Now, one consequence of tail recursion and cons-freeness, which is not trivial to see, but is proved in the paper, is that every monadic constructor TRS is equivalent to a monadic constructor TRS with at most one defined symbol in the right-hand side of every rule. So you can actually create an equivalent CTRS that has at most one defined symbol on the right-hand side. But then intuitively you're done, because we start with all in this whole setup of accepting strings with a term that has one defined symbol, namely the start symbol applied to the input. And then if you use this equivalent CTRS, you end up with a new term, no matter what you rewrite to, that has also at most one defined symbol. And then you continue. So at all times, in all rewrite or reduction sequences, you have at most one defined symbol. This is like the state of a finite automaton. And since you're cons-free, you cannot introduce new things to the input. You can just kind of slowly chip away at it. So this looks very much like the execution of a DFA on NFA, and that's basically the entire key. So that's the intuition behind all of the results. So what's the conclusion? Well, all 4 classes of the Chomsky hierarchy are completely characterized by monadic constructor TAs with natural restrictions on the rules. And this is another step in gauging the expressive power of certain natural restrictions on rule formation. For instance, the notion of constrainedness that has been used for characterizing many other more advanced classes, like complexity classes such as P-space, X-time, and NP. Now, a couple of items for future work, or food for further thought, if you will. We can do this for many other languages that are not in the Chomsky hierarchy, right? The Chomsky hierarchy is from 1956, and vast advances have been done in formal language theory. For instance, we now have the visibly push-down languages and so on. And my guess is, or my conjecture is, that you can do similar, very, very simple restrictions and get characterizations of those classes of languages as well. Secondly, there are very likely analogous results in pure string rewriting to be investigated, but you need to define what you mean by characterizing a language by string rewriting. So you have to come up with reasonably good definitions for this, and then things don't become quite as easy as, for instance, characterizing context-free languages by just taking a context-free grammar and reversing all the production rules. You need a bit more creativity, I believe, to make this work in a very clean way. So that's it. Thank you very much for listening to the talk. And at the live talk, I'll be happy to take questions. Thank you very much.
Okay, we thank the speaker. So, Jacob, can you? Okay, you're there. So, is there any question in the audience? You can just raise your hand. Okay, I have one. You can unmute yourself because you're a co-host. So please, Rafael, go ahead.
First of all, thanks for the talk. I had a little question. So using the strongly cons-free definition, it fits perfectly, you know, with the idea of a push-down automaton. But if you take the usual, you know, not the strong cons-free definition, does it mess up like the stack? What would be the so the expressivity changes?
Yeah. So the question is whether the expressivity changes if we use cons-free systems that are not strongly cons-free.
Yeah.
So the problem is not so much the stack as it is rather the fact that if you have an ordinary cons-free system, if you can introduce new constructors that also, well, not new. If you can include certain sequences of constructors that are either present in the input itself or are constants of some sort, especially if they're unary symbols, then it does not as much mess up the stack as it becomes a lot harder to see how to cleanly model this using a push-down automaton. So basically that direction. It does something to the stack. Maybe that is the correct way to phrase it. But I wouldn't say that that's the main problem. The problem is that it really introduces noise that have to be treated in some way. I think that can be done, but I simply didn't do it in this paper. I think I have not proved it, but I would very strongly conjecture that the expressivity remains unchanged if you just use cons-free systems.
Okay, yeah, you're just cutting down the unnecessary.
Yes, I am, and in a sense, this result is much more elegant because it's easy to explain to people, right?
It fits, the two parts, it fits perfectly. Yeah. So I was wondering, you know, if you, it seems like almost fragile, you know, if you add just something, it's not so perfect.
Yeah, and I think that's actually an excellent remark. I do think that some of these results are actually fragile. So typically we would like results that are robust enough that fairly trivial changes to the syntax don't change the characterization, right? This is what we want. And I think that and this is purely this is anecdotal. I don't have any concrete proof to back this up, but I have noticed, especially in these characterizations using only unary symbols, that things turn out to be a lot more fragile or brittle than if we just take general systems. Because in general systems where you can always intuitively, you can always, well, just throw in some more function symbols to put the junk in, something like this, right?
Yeah, you sweep it under the rug.
Yeah, and this is harder here. So I think that if you were to play a bit around with these characterizations, you might actually create some smaller changes, maybe not const-free versus strongly const-free, but other things that would actually break these results. So I do think that they're fragile, and I think this speaks against the strength, at least, of this paper in particular.
Thank you very much.
Thank you. We thank the speaker again, and of course you can meet Jacob in the break room for this paper, or in the coffee break after the session ends. So thank you, Jacob, and